Okay, good afternoon. So today let's continue talking about orthogonal matrices, and then we're going to talk about inner product space. First, let's have a warm-up problem. U is this matrix, theta is a real number, because its angle you can think is from 0 to 2 pi. Now I ask, if I give you two vectors, U and V, they are in R2, and I ask whether the inner product of U times V, U dot V, is equal to UU dot UV. So let me try to launch the poll.
Sorry, Professor, what does the V with a line through it mean?
Sorry?
What does the V through a line through it mean?
V through a line? Sorry, I don't.
With a line through it next to the U.
I don't. Yeah, I mean, so you mean U matrix? I don't understand. So there's only U matrix.
I think he's asking
It's for all.
yeah.
Sorry. Could you say again?
It means for all U and V.
Yeah, for all, right. Oh, this one. Oh, for all. Sorry. Yeah. Wait, let's wait for 20 seconds. Ten seconds. Okay. So most of you think this is correct. So let me explain. We just actually we did that before, but it was the beginning of chapter 6. So now it is a good time to think about this again. So let's start from the right-hand side. So first of all, this is true. And the right-hand side is U transpose UV. And this becomes U transpose UV. Now, as you can see, if we can show this as an identity matrix equal to I2, then this is going to be U transpose V, which is U dot V, right? So let's compute U transpose U. So this is cosine theta square plus sine theta square, and this is 1. Then there's a cosine theta sine theta minus that, which is 0. So this is 0, and this is 1. So direct calculation shows that this is I2. Therefore, the right-hand side is equal to U dot V for all UV in R2. And therefore, it is correct. So this, we have seen at the beginning of chapter 6 that this allows us to define the inner product and the angle. And this is indeed true, because this matrix is nothing but the rotation matrix in R2. Rotate everything by angle theta. And we know that what this means is if I start from some vectors u and v. After some rotation, so u becomes, it doesn't change its norm, becomes u prime, and this is theta. V is also rotated by angle, which becomes v prime. Then the angle between u and v is really the same as the angle of u prime and v prime. So what this shows, you can see that has nothing to do with R2. If you go to any Rn, this also works. Therefore, if U is an orthogonal matrix, which means U transpose U is In, then it preserves the inner product and therefore also the angle. Any question? Okay, so far we have talked about we started from the inner product in R2 and R3. We went through the inner product in Rn, the Euclidean space, and the standard Rn. And then we talked about the projections, Gram-Schmidt process, least squares problem, and this orthogonal matrix. And all of them are in Rn. So as we said before, so this is really, you start from a standard vector space, and then you equip it with inner product, so that after this, it becomes an inner product space, but everything so far has been restricted to Rn. But in chapter 4, we have learned that the definition of the vector space can be very versatile as long as it satisfies these axioms from 1 to 10, and you just check, and you will find that this is indeed a vector space. Similarly, we can generalize the idea of the inner product space to something that is not only Rn, which is this guy, but all sorts of other things, and which is we have defined different inner products for different vector spaces. So today, what we want to talk about is really this general inner product space. Maybe I should say something which is logistics, and I have mentioned in the announcement that there will be a updated course policy coming out in the next few days. That was when I sent out the announcement on Tuesday or something. But apparently, the department just had a meeting yesterday, and there are certain unforeseen legal challenges from campus and the department, and therefore they are currently revising the guidelines. Those will have direct and a potential huge impact on all the lower division classes. So after discussing with the GSIs, I think it is better for me to just hold the course guidelines and updated policies for the moment. And hopefully the campus and the department will be able to come up with a solution in the near future. So stay tuned. Okay, so let's just say now that we define what is a general inner product space. So an inner product so first of all, what is an inner product of a vector space V? Is first of all, it's a function that maps a pair of vectors remember, vector is just an element in V, UV, in the vector space V, to a real number. It can also be complex. As I said in this class, I just say everything is in real without loss of generality, but it could be a complex number as well. Denoted by UV. Okay, so this you can think is nothing but a notation. You can think I can also call it FUV, but F is so general, so it maps two things from V to a number. But I just instead of calling F, I use this angled bracket. It's purely a notation. Satisfying the following properties. One, so UV should be equal to VU. Let me put this bar here, which is congregation. This means that if, so to be clear, if there's a real number, then conjugation doesn't do anything. If there's a complex number and you conjugate that, which means A plus IB becomes A minus IB. So in the real case, just means that this inner product is just commutative. 2, U plus VW equal to UW plus VW. And for all these properties, and you should really think in terms of the inner product in Rn, and you will find that these are indeed pretty natural. And 3 is CUV. So if I have a number here, and this is equal to C bar UV. Again, if it is a real number, you don't need to worry about that. In the case it is a complex number, you need to add this conjugation. I'm going to comment on that later. And 4 is this one, where I consider the inner product of a vector with itself, it is not only real, but is also non-negative. Furthermore, this is, if I say this inner product with itself, which is like the length is 0, this is equivalent to that U is a 0 vector. So, here, as I said, this is a complex conjugation. That is, this C bar is for the complex case. So these are the 4 properties. Okay, so it's just like vector space. You have this 1 to 10. You have here this 1 to 4. If it is satisfied, all the properties are satisfied, then it is called an inner product space. The rest of the class, we're just gonna go through various examples, and we can see what kind of things are the inner product spaces and what kind of things are not. One thing I want to comment is this 3. I mean, where did this C bar come from? So comment on 3, which is I can try to find a rule for UCV. Okay, so if I, on the right-hand side, I multiply by a scalar C. Here, C is a complex number. Okay, so this is a complex number. If it is real, then probably it's just the same answer. The question is, if it is a complex number, whether this will still be the case. I don't know the answer, but what I do know are the property 1 and the property 3, they hold. So this one is equal to, CV U bar. This is by property 1, right? I just exchanged the order. Now, I use property 3. This is equal to C bar V U bar. Okay, but sorry, the whole thing bar, because here you have a C bar, but outside you have a overall. And the complex conjugation for two numbers, so C1 bar, C1, C2 bar is a C1 bar, C2 bar. So this one is, I use 1 again. This is C, because the conjugation of conjugation itself. Then this one I use 1, so this becomes UV. So you see, be very careful that if I multiply a complex number on the left-hand side of the inner product, the rule is that this should be the C bar. And if it is multiplied on the right-hand side, then this should be C. Any question? Okay, so now let us start to look at some examples. One is let's see. Let's say we still start from Rn, but try to define some different inner products. So UV is in R2. I define inner product to be U transpose A V. I ask, is this an inner product on R2? It's a difficult question, so you need to think a bit. And A, B are just some arbitrary real number. What you need to do is to follow 1 to 4 above. Let me just make it smaller so that you can see everything. You want to check 1, whether the 2 commute, U plus V, scalar, and 4. If it's not true, all we need to do is to find a counterexample. A hint is A, B can be anything, so you do need to pay attention to the corner cases. "30 seconds. 10 seconds. Okay, so it's more or less half-half, slightly in favor thinking it is false. The true answer is indeed it is false. So how do I know that? All I need is a counterexample. Say I take A to be a zero matrix. Okay, which means that the values of scalars A, B are 0. Now I have I take any for any UV vector that are in R2. The inner product defined in this way is a constant, that's 0. So so in particular, if I just take any U, then UU is always 0. But this does not imply U is 0 vector, therefore violates property 4. Property 4 is really, as you will see from a number of examples later, is the most tricky one. In many cases, 1 to 3 are easy to see, but really what it makes it fail is property 4. It says the length or the square or the inner product of vector with itself is 0. It must imply U is a 0 vector. In this case, it does not. Any question? Okay, let me now revise this problem. So same problem. But now I constrain A and B, they are positive numbers. The question is it an inner product on R2? Poll again. So, sorry, I need to end it first. Now I relaunch. Thirty seconds. Fifteen seconds. Okay, so share. Okay, so this time it's overwhelmingly it is the favorite result is true. The answer is indeed this time it is true. How do you show this is true? 1 to 3, check by yourself. All I need to do is to show 4. Now give me a vector U in R2, then U transpose AU. This is, let me write U to be U1, U2. these are two of its components. This is u1 square a plus b times u2 square. If this is 0, because both terms are non-negative, we have a u1 square equal to 0 and bu2 square equal to 0. Therefore, u1 and u2 are both 0, which means that u is a 0 vector. So, inner product. Any question? Okay. Now, we really want to go beyond Rn. Look at our favorite non-Rn example, Pn. Let me remind you that Pn is the vector space, consists of all the polynomials of degree up to n. So Fg, take any two polynomials. I define the inner product to be the integral fx gx dx. Okay. And the question is whether this is an inner product. Let me do that again. Thirty seconds. Okay, so again, it's kind of half-half. So the answer is, I don't know, so let's check. So 1 to 3, those are linearity and other things I'll leave to you to check. The answer is yes. Now we directly check 4. Four means that I take any polynomial from V. Now I have ff. This is equal to 0, means that this is f squared x dx. So if this one is 0, because every term is, at every point, this is non-negative. It is a square of something. And so f is a polynomial, so it is continuous. So it must be 0 everywhere. And this one is the 0 polynomial. You can say f is 0, and this is the 0 vector in B. So 4 is indeed satisfied. So this is an inner product. Any question? Another example. Same setup. Inner product has changed. F prime x, g prime x, dx prime means derivative. One minute, only check for whether this is inner product. Okay, so most of you think this is incorrect. This is not in a not in a product. The answer is indeed false. To show this is false, all we need is to find one function that is not a zero vector, but its inner product is 0. Let me now take fx to be a constant function that is 1, which is not a zero vector. Now ff, so this is the derivative of that is 0. So this is 0, so does not show f is a zero vector. So this is not an inner product. Change again. Same setup. Fg is 0 to 1. They say, wait a minute, this is exactly the same problem. Modify it. Plus, so this is a parenthesis, plus the value of f evaluated at 0 and the value of g evaluated at 0. Question is whether this is an inner product. Okay, so this is again a tricky question. So the answer is about half-half. So let me say again, we check. So 1, 2, 3 has been checked. Now we check 4. So to check 4, we have f is a polynomial. We consider the inner product with itself is equal to 0. F prime x square dx f0 square. So this is indeed a non-negative. If it is 0, I want to show f is indeed 0. But this is again the addition of two non-negative things. Therefore, I have both the square of the derivative is equal to 0 and f0 square 0 or f0 is 0. Following the same argument, we know that f prime x squared must be 0 everywhere on 0 to 1. But this is a polynomial, so it can only have up to n roots. So this is a f prime x, which is in Pn minus 1, is indeed always equal to 0. Now, by the fundamental theorem of calculus, fx for at any point x, I can link it from 0 to x, and this is fy dy prime plus f0. But this one we have just shown that is always equal to 0. This one is 0, so this is equal to 0. So indeed, f is a 0 vector in V, so this is an inner product. Any question? So through these few examples, you can really see that the inner product, whether it is inner product space, it really depends on the definition of your inner product, although the underlying vector space doesn't change at all. So that is why when we say we equip a vector space with an inner product is a very precise characterization of the procedure. You can have the same vector space. I can just give it different equipments, and it will just become different inner products. So inner product spaces. In particular, if you continue taking lessons such as Math 104, and you will recognize that what we just talked about before, the two vector spaces are really, one of them is called L2, which is consists of all the functions, and such that the f squared x dx is less than infinity. This is an inner product space given by this thing. This is the corresponding inner product. And I can change that slightly for the H1, 0, 1. These are, this is a space consisting of exactly these functions, which is f dx squared plus, I mean, not exactly that, but 0, 1 f squared x dx. You can try to think what is the corresponding inner product, so this is and this defines a new space, but these are quite optional. Just illustrate here for your interest. If you continue to learn along this line, you will learn this encounter this inner product spaces. So now that we have defined inner product, if you, just like in chapter 4, once we have established the idea of vector space, it only took us a sentence to translate everything we have learned in chapter 1, chapter 2 to chapter 4. So now I have really defined what the inner product is. That is really, that definition has done the heavy weight lifting. We can now just translate everything in chapter 6 from Rn with the inner product to a general vector space with an inner product. This includes length, which is the you take a square root, right? Give me any u in V, its length is defined with this. You can also use the notation this as the length. You can talk about angle, because that's just the arc cosine. So that's like the arc cosine of u dot V divided by u, length of u, length of V. I can talk about orthogonality. Because I've already got the inner product, I used the u, this one. Let me change this. So if UV is 0, then I can say U is perpendicular to V. This has nothing to do with Rn anymore. We're really talking about a general vector space. So we can talk about a polynomial f is orthogonal to polynomial g, and it will be in this sense. Because I can equip the polynomial space with different inner products, if two polynomials, they are orthogonal in some inner product space, it is not necessarily the case that they are orthogonal in some other inner product space. With inner products, I can also define projection. I can define Gram-Schmidt. I can have the uniqueness of the projection. I can have the best approximation, because everything just depends on the definition of the inner product. And I can talk about the least squares. Again, what does least and best, what do they mean, really depends on the definition of the inner product and the definition of the length. In one inner product, you say this approximation made the least amount of crime. It doesn't mean that the same conclusion would hold true if you change the definition of the inner product. So, any question?
Yeah, Professor, I had a question.
Yeah.
For P, what is the common inner product definition? Like you have one for Rn, what is it for P?
There is no common inner product, so you have to specify what kind of inner product you're using.
Okay, so there's not one that's like generally accepted.
There are some, but still you need to. It's not like the Euclidean inner product. You can just say, yeah, Rn is an inner product space. For Pn, you do have to specify what kind of inner product you are talking about.
Okay, thanks.
For example, both the L2 and H1, they're very reasonable inner products. Okay, so let's take a look at the example. So I have three polynomials. One is 1, the other is x. The third one is 3/2x squared. And now I want you to orthogonalize, which is Gram-Schmidt, with respect to the inner product Fg 0 to 1, minus 1 to 1, Fx gx dx. So first of all, we need to make sure that this is indeed the inner product, but we did nothing other than changing from the domain from 0 to 1 to minus 1 to 1. So you can convince yourself that this is still inner product. Next, we do the Gram-Schmidt. Let me call the new vectors, call them Q1, Q2, Q3. So apply Gram-Schmidt to the polynomials. Q1 is always easy. I just take it to be P1. I can scale it. That's also fine. But without loss of generality, I take it to be P1. Q2x, it should be P2 minus, so this should be QP, and this should be a QQ, Q1, Q1, Q1. Q1x. It's very similar to the Gram-Schmidt. And what's the inner product between Q1 and P2? Sorry. So Q1 and P2 is the integration from -1 to 1. And this is 1 times x dx. So x is an odd function with respect to a symmetric interval. So this is 0. So we have, this is nothing but P2, so x. Any questions so far? Good. Q3, follow the same procedure. P3, project P3 to the span of Q1, Q2. Q1, Q1, Q1x minus Q2, P3, Q2, Q2, Q2x. See, although we have changed to the polynomials, but the procedure is exactly the same thing. So let me compute. So Q1, P3, this is -1 to 1, 1 times 3 over 2x squared, and dx. So this is really, so I have a 1/2. So this is a even function. So this is 0, 1, 3x squared dx. I changed the integration range. And this is dx cubed. X cubed, 0, 1. So this is 1. Okay. So this term does not vanish. Any question? Since this term doesn't vanish, I also need to compute the denominator, -1 to 1. So this is 1 times 1 dx, and this is just 2. I also need to compute this. Q2, Q3. And this one is -1 to 1, x squared. But again, this is an odd function, so it's 0. I don't need to worry about that. Q3x is 3 over 2x squared minus 1/2. So now we have concluded Q1, Q2, Q3 is orthogonal with respect to the inner product we defined. Is with respect to this particular inner product that we defined. So actually these three functions, 1x and 3x squared over 2 minus 1/2, it actually has the name. They are this first three so-called Legendre polynomial. Legendre polynomial is a set of orthogonal polynomials with respect to the L2 in the product. And how do you obtain that? Is exactly how do you obtain the Legendre polynomial? Is really you just take x squared to xn, and then you just apply Gram-Schmidt, then up to a normalization constant. So you might wonder, where does the 3 over 2 come from? That's just a normalization constant. The same material. We have this Legendre polynomial. And what you have seen are just the first three. And again, this in the Gram-Schmidt with respect to the L2 in the product.
Would the Legendre polynomials be different for a different integral range in the inner product?
Very good question. The question is whether Legendre polynomials are different with respect to the range and inner products. The answer is yes. Actually, more specifically, Legendre polynomials are specific to the range to be -1 to 1 in the product is this. This is called a Legendre polynomial. If it change to a different inner product, it's just a change to some other polynomials. Any other question? Okay, so we have finished everything regarding chapter 6, and then next week we're gonna talk about chapter 7.